Hello everyone and welcome to our Open Science Skills Makeup. My name is Cameron Riddell and I will serve as your instructor for the day. Now, today we will talk about open science as it relates to your work that you do and other work around you. And what that means is we are not simply going to talk about open science, how it might benefit you, but we're going to talk about how open science can benefit the work that you're already doing, and you can actually reap more benefits from that, and how you can approach this topic in a digestible and understandable manner. And in fact, open science is this transformative movement that is aimed at increasing and making research more accessible, reproducible, and inclusive. And to understand that, let's go ahead and dive right into the material that I have prepared to share with you today. And so to do that, I'm going to start by sharing my screen. So behind me, you'll see my screen, and I'll hide in the corner over here. As I said, open science is a transformative movement that's aimed at making research more accessible, reproducible, and inclusive. And it's not just a philosophy, but it's a practical framework that promotes transparency, collaboration, and the democratization of knowledge. In this session, we're going to explore the foundational principles of open science while discussing the key reasons why it matters for researchers across all disciplines. And by embracing open science, you can amplify the impact of your work, foster interdisciplinary collaboration, and address critical issues such as inequities in access to knowledge and reproducibility crises in research. Our journey will also introduce several tools and practices to help you implement open science in your daily work. We'll cover platforms for sharing data, code, strategies for publishing open access, and techniques for engaging with open peer review. Whether you're a seasoned researcher or just starting out, this session is going to provide you with actionable insights to help take the first steps in integrating open science principles into your research process. And together, we'll discover how making open science isn't just good for your field, it is good for science itself. So let's go ahead and take a look. Now, as a reminder, by participating in this session, you have the opportunity to earn your Open Science badge. That is your NASA TOPST badge. And how you can do that is once you complete this session, you will have the knowledge to take on our quiz, which we have already emailed to you. So after the session ends, I would encourage you all to take the quiz and get your Google form submitted so that you can earn your NASA badge. In order to earn this badge, you must score at least a 70% on your quiz. So make sure that by the time you take that quiz, you are good and ready. You have studied up on the open science concepts. And I promise you the quiz is not that long. In fact, I think it's somewhere in the realm of just 10 to 15 questions. So I know that you all can do this, and I know that you all can earn your open science badge. Before I jump into our agenda, I want to provide just a brief background on who I am so that you all know who's going to be talking to you for the next few hours. In fact, we're planning to take just under 3 hours, and we might even finish up a little bit early. And if we do, you are all free to go a little bit early, and I will let you know if that happens. For those who don't know me, my name is Cameron Riddell, and I am a academic researcher where I used to study human memory and psychology, and I have been turned into a technical programmer as well as a consultant and instructor. And academic research has always been one of my passions, and when doing that, it was so frustrating to see papers that didn't reproduce, even if it was my own work, and I am not perfect. So sometimes I would have trouble thinking back of a few years and being, oh man, I did that experiment. Where are the data? What have I done with them? But it's not about, or I should say, open science is not about saying you should have been doing your work this way all along. It is about what things can we start integrating into our life today so that we are being more transparent, open, and accessible for tomorrow. And so today, I would like for us to cover 4 important questions. Those questions are, why is open science important? What does open science look like? What tools should I know to participate in open science or ease your participation in open science? And then finally, how do I participate in open science? When we talk about our first question, why is open science important? We're going to talk about a lot of the open science concepts that you'll encounter, things like your fair and care principles, as well as a little bit of perspective and discussion of what is currently wrong with our academic, or I should say, our research model. Then we'll talk about what does open science look like. When we talk about this question, we are simply going to go through a framework for envisioning open science and how we can use, make, and share all of the work that we're doing, or of course using work that other people have done and doing it in a responsible and ethical manner. Then we'll talk about tools. Here we're going to cover a lot of things. We're going to talk about programming languages and version control, in addition to actually searching and finding a data set to use. How do you go about uploading code or data to an archive service? Those are all of the things that are important for us to be able to do. And so we're going to talk about the tools and do a few demonstrations to show you how easy it is to use some of these. Finally, we'll talk about how you can participate in open science, and this will be our wrap-up for the day. But I'm going to give you just a few starting points, small things that you can integrate into your work. So as I said earlier, you can start doing open science today so that your work is more reproducible, more transparent, more ethical for tomorrow. And on top of all that, at the top of each hour, we're going to take about a 10-minute break. So I'm not going to sit here and lecture to you for the next 3 hours. What I want you to do is get typing in that chat. And in fact, I'm going to prompt you all for a couple of questions. We have our chat here on our platform, so you can absolutely use that chat, and I will message you back in our tea breaks. So sometimes the chat moves a little bit fast. It's hard for me to get to. And if there is a question that you want me to answer, then please do ask me that question during our tea break, and I'll make sure that I give you a message response right back. With that all being said, let's go ahead and jump into our very first question of the day. Why is open science important? Well, the first reason why open science is important is you should support your own arguments. And in fact, I think this point stands on its own. If you have ever been in a discussion or a debate with another person and they start either resorting to sharing facts, then you're going to ask them, well, where did you get that fact? And you're going to ask them to cite their sources. And we do this already, right? In the current academic or the current research model, we of course cite our sources. But one source that is incredibly tricky to cite is my own methodology. If I tell you, well, I took these data, I divided them into 2 or 3 groups, and then I performed this statistical test, I can tell you that I did that. But how do you know that I did that with intense rigor or statistical understanding, ensuring that I did everything correctly? And what you would want to do is say, well, Cameron, it's great that you told me, right, that you performed this statistical test, but I'm really curious, can you show me how you divided your group, your population into 3 groups, or your sample into 3 groups, and then can you show me how you actually evaluated that statistical test? What specific parameters did you do? How did you go about doing this? And so we can accomplish this perspective of showing or supporting your own arguments by participating in open science, and importantly, what we need to be doing with every single publication is not just checking a box that says, well, code and data available upon request. What we need to do is start supplying those code and data alongside the publication or releasing them on a different platform at the time of publication, and we should be doing this at the very least. Because your code and your data are the ways that you show your work. There is so much, and I know that you all know this, but there is so much that happens in a given experiment that when it comes time to write your article or your paper for your publication, you kind of sweep it under the rug. And research is not this tried and true, beautifully polished thing. In fact, it is messy, and we want to be transparent with that mess. What hard corners did we run into? What things that we were not expecting arose? And we can be very transparent with this. And part of the solution here is that we can share our code, we can share our data, all of the materials that went into coming up with our final publication in support of our arguments. And so there's really nothing additional to be said here. If you want to be able to support your own arguments, then you should absolutely be releasing code, data, anything that's helped you in your analysis, and not just talking about it. Show it. Another reason that we would participate in open science and why this is so important is many fields. And I know this, my background psychology, we are perhaps psychological researchers, especially a couple of decades ago, maybe most susceptible to this, but I know many other fields are also subject to a reproducibility crisis. And in fact, if you think your field has undergone recently, or maybe half a century ago, a reproducibility crisis, please let me know in the chat, because I want to know what fields besides psychology is having issues either reproducing individual studies or issues replicating broader concepts at large. And so the reproducibility crisis stems from this concern that most current published research findings are false. And the probability that any given research claim is true might depend on study power and bias, the number of other studies on the same question, and importantly, the ratio of true to no relationships among the relationships that you probed in each scientific field. And all this is going to say is, if you give me, your code and data, am I able to get to the same results that you got to in your publication? And I think this should be the foundational, at the very least, we should be able to do this. Because if you write up the most beautiful and convincing paper, then I just have to trust you at your word. But as soon as I get my hands on your code and data, this code doesn't run on my computer, or I get a different set of results, thus leading me to say, well, what did you do with this data set? Is there some filtering or something that I missed? And this is why it's so important to be transparent, because we can figure out why things don't reproduce. But we also want to make sure, of course, these things do reproduce in the first place. Because by being able to reproduce publications or ideas or results, we are able to build up more confidence in that thing that it is true. If you give me your code and data and I'm able to reproduce the results that you obtained in your study, then I'm more inclined to believe, your results, and thus I'm more inclined to accept your conclusions as at least partially true, Because I don't know if we ever fully agree with somebody else's conclusions. That is what it is to be a scientist. We want to be inquisitive and questioning at all times. But many fields are undergoing this reproducibility crisis where papers are failing to reproduce, or ideas are failing, individual studies are failing to reproduce. Now, I haven't mentioned the second term just yet, but I also do want to let you know about the difference between these two often conflated terms. We often talk about reproducibility and replicability. And let's establish some definitions so that you all know how we are going to be using these terms for the remainder of our session today. What reproducible means is reproducible means that you are able to obtain consistent results using the same input data, computational steps, method, and code, as well as conditions of analysis. Replicability, on the other hand, means that you are able to obtain consistent results across studies aimed at answering the same scientific question, each of which has obtained its own independent data. And so a reproduction or reproducibility means that if you conduct a study, you collect data as part of that, maybe you write a little bit of code or you perform some type of analysis. Can you get me from your original inputs to your results? And can you do that with the products that you have shared, or I should say the artifacts that you have shared, your code and data? Can you do that? Can you reproduce your own work, importantly? And I want to challenge you all. Go back to a study or a data set you collected 5, 10 years ago, or even 1 year ago, and try to get to the same set of results that you published in your paper. If you cannot do that within a reasonable amount of time, within an hour, then that means you are not set up to be reproducible. And there are many barriers to this. I've talked a little bit about, maybe the code not working. But I will say this, is if you share your code and data and it is an absolute mess and it takes you an hour just to untangle kind of the mess of files and folders that you have, think about how hard it's going to be for somebody else to reproduce them. And so computational knowledge is not the only barrier to reproducibility. It is a large barrier, but it is not the only one. Being organized is also something that we want to do when we are managing our digital assets. But that's something we'll talk about much more in depth later on. So that's reproducibility. Our replications or our replicability means that at a broader level, are we able to replicate concepts? And typically concepts are things that span multiple studies. And so what we want to do is, if I find something really cool about psychology, I take 40 participants, I do some study on them, and I say, whoa, I found this awesome thing. It's in my best intention, and it's in others' best intention to look at that as an individual study and say, okay, that's interesting that you found this really novel or really cool thing. But can I change it, right? Can I take 40 of my own subjects, right? 40 different participants, test a really similar or the exact same question with a small extension, and then observe the same cool result that you did. And so this is what we want. We want our concepts to be able to replicate. We want to be able to take something that we think is insightful, novel, or cool, and we want to be able to run a similar study and find that same thing. Because if you are able to find that same thing with a completely different data set and a slightly different methodology, it increases the likelihood that this thing is some measured truth about the world that we live in. And it gives us further lines of questioning, building off of a confident baseline. And so for anything that is new or novel, we always want to make sure that these things replicate. And something that is becoming increasingly popular in the psychological research field is self-replications. All this means is, if I take my previous example, 40 participants, and I found something I think is really neat, then I should probably do a follow-up study, right? Where in this follow-up study, I get 40 new participants. I test that same, I use maybe the exact same or a similar methodology with a small extension, and I get to the same conclusion. I'm trying to replicate the previous study. But on top of that, maybe I'll add some extension. I'll say, to what degree does this third factor moderate that original neat or interesting thing that I found? And by doing this, I've actually come up with two unique studies that I'm performing, but they are conceptually linked such that the second is a replication of the first with an additional component. And by including this additional component, you are actually justifying to grant reviewers that your research, if it pans out, is going to hopefully replicate, but you're also showing your reviewers, these grant reviewers or your advisors or things like that, that you are being very rigorous in mind. You're saying, well, if I do find this cool thing, then I'm going to want to make sure that it is actually something that could be true before I go tell the world about it. And so often you see psychological experiments having multiple studies in a single publication, but each of these multiple studies will often replicate previous findings and build on them to build a stronger, more thought out narrative. So reproducibility is reproducing a single study by having the same code and data, and replication means you are creating the same concepts or the same result sets from independent data sets that all, of course, have some similar methodology. Well, we've talked about that open science is about supporting your work, being transparent. We've also talked about the reproducibility crisis and how being more transparent can help with that problem. But another thing that comes up is closed science is simply difficult to validate or refute. And the broad idea here is that we are being transparent and we're being open so that others can be more effective with our work and we can make stronger decisions about whether or not we believe something to be true. And in fact, in this example, I stand by that closed science, the way we currently do things, is difficult to validate or refute. And the reason for that is something I said earlier. When you come out with a publication, it is so easy to sweep anything that went a little bit funny or wrong completely under the rug, such as the case in this example. This comes from a study that was conducted in 1990, and it had to do with understanding, right, atmospheric warming or climate change, as it so turns out. And in fact, this study in 1990 came to the conclusion that, well, I'm not observing any warming or any change in the Earth's atmosphere. And so I don't think we really understand climate enough to change climate policy, right? This is a strong conclusion because this is something that can be used by your government to then reserve making judgment or reserve passing policies. And so we'll talk about this idea a little bit later, that science is not just about you and your work. It's much broader than that. But I will say, this particular paper published in 1990 was used, right, to say, well, maybe we don't actually understand climate enough to really be making decisions about climate policy. Being reserved, not a bad thing. But one thing that this paper did not do well, and I will give them the benefit of the doubt. In 1990, sharing your code and results or sharing your code and your data, not an easy thing to do. You had to jump through a lot of hoops to do it. But for this 1990 study, they shared their data. It wasn't very easily accessible, but that could be just, a product of the time. But they did not share their analytical code. And in fact, 8 years later, in 1998, there was an error in the analysis that was discovered, or not necessarily discovered, but theorized, because you don't know what the original analysis looked like at the very smallest level. And so what other researchers or other scientists had started guessing was that in this 1990 paper, the original authors didn't account for orbital decay and other effects, which introduced an artificial cooling trend in the upper atmosphere, right? So what this then means is that in 1990, the publication came out with some conclusion. 8 years later, scientists got thinking, you know what, I don't know if this is right, and in fact, I'm willing to bet that they didn't do this thing particularly correctly. 5 years after that, in 2003, these researchers who were questioning this original set of conclusions or the analytical method then came out with their own approach where they actually reproduced the results. So they were able to take the original inputs from 1990, the original data, and they had their own completely recreated code that then got to the same set of results as the original 1990 paper. This took 13 years to do, which is an incredibly long time. And I will say that in parallel with this, they also released a modified version of that recreated code such that they fixed the error that they thought they had detected, and they got to conclusions at least that were more within their own purview. But this process took 13 years, right? From original introduction of the paper or publication of the paper to in 1990 to 2003, when we were finally able to say, you know what, this is what the code looks like, and this is the error that the original authors made. And I don't know about you, but you can think about all of the time and money that was spent in that 13-year timeline in order to either combat or support the position of this original 1990 paper. That sounds like a lot of effort to put in for something that didn't reproduce correctly or reproduce strongly on its own. And in fact, because the method section, right, was missing some of the key details here, these are the things that end up getting swept under the rug. These are the things that are left out of the analysis that are actually key and pivotal, although they might seem small at first because you trust the researchers to have known that they included or excluded specific variables or specific factors. But at the end of the day, nobody is perfect. No group of collaborators is perfect. We forget things, whether intentional or not, impossible to say, but we forget things. And maybe there's some sort of contention in the field. Maybe this correction at the time was something that not everyone agreed on was the best thing to do. But what you can do is be transparent with your work, because this should not have taken 13 years to resolve. And in fact, in a more modern comparison, I have seen papers that have gone from publication to somebody saying, you know what, I think there's something wrong in the code in just a matter of months. And that is only attainable by sharing your code and your data, the digital artifacts on which your arguments are based on, alongside of your arguments. And really, your publication is an argument because you're often going from some set of observed data, and then you are generalizing and drawing conclusions from that set of results as well. So this is another reason to participate in open science, because we want our work to be able to replicate, we want our work to be sound, and we want our work to be able to be investigated by others such that we can build a stronger truth. Now, this is a point that's incredibly important to open science. However, it is also the scariest point. And this is why we often end up sweeping things under the rug in our papers, because we're not 100% certain that the things that we're doing are the correct things to be doing. And so we want our article or a publication to be this really snazzy, buttoned up, very well-dressed argument. But as I've said multiple times, research is messy, and we need to be transparent with any mess that goes on. And in fact, research is not just about you. It involves many other individuals and stakeholders. So although researchers might be in the center of this cloud of roles or individuals or people, research doesn't just affect you, and it doesn't just affect your colleagues. In fact, we envision, I should say, that research involves three broad groups. That is the researchers themselves, policymakers, and the general public. And if you envision research as influencing each of these groups, right? Researchers come up with ideas, and they provide and create results as well as conclusions. Then another group or another set of individuals, most often scientific journalists or educators, then translate that set of complex results into more distilled concepts that we then share with the general public as well as policymakers. And policymakers help guide or apply research findings for the betterment of society, and the general public then helps with voting to determine what pace or what trajectory research goes on, what should be funded, how much funding should research be provided, how much funding should these new policies that are being derived or created based on research receive, how important is this to us? And so these three groups are always interacting with one another. And if you have ever communicated with another individual or another entity, then you will know how important it is to be transparent in that communication. And so we want to be open and transparent. We want to be forthwith and not reserved with all of the things that we are doing work on. So that is why research is not just about you. Everything that you do as a researcher is going to have some broader impact. And you need to be aware of that, and you need to be transparent with how you came to your conclusions so that others can investigate how deeply they're going to trust your work. And in fact, another reason that it's so important we participate in open science. We've talked a lot about, supporting your own arguments or examples of why the current paradigm, the current way we do things is just simply going to cause us more work and more headache down the line. But a benefit that you get directly from participating in open science is that you can receive more credit for the work that you are already doing. And what this means is if you've ever planned an experiment end to end, so if you've run an experiment completely on your own or maybe with an advisor or a collaborator, then you'll know that there are so many things you need to do. All the way starting in the planning phase where you have product ideation, design, or other details around your planning that you're going to do, to your implementation phase where you might require some training, or if you're creating a methodology, you might need to create some training, or train your research assistants in order to work effectively with you, or train grad students, or train postdocs. You'll also embark on data collection, as well as data wrangling, as well as data exploration. Not necessarily all in that order, but what we can see here is that you are doing a lot of work. And in fact, all of this work creates digital artifacts, right? So for your planning phase, you're going to be creating proposals, data management plans, codes of conduct, depending on your collaborative nature. Then during your implementation phase, maybe you'll be creating tutorials or guidelines. You'll collect data. You'll generate metadata as a result of that collection process. You'll create some type of analysis pipeline. You're going to write some analytical code, maybe create some software or Python or R notebooks. You're going to create some archives, right? In open science, you're going to be creating archives, that's for sure. And in these archives, right, you're going to be putting your code and your data and anything that you want frozen in time so that others can cite it appropriately. And in fact, on top of that, once you share all of those things, you should be self-promoting. You're going to be, of course, publishing papers, but you're also going to be giving talks, writing blog posts, maybe recording videos, or writing tweets or X's, or I'm really not sure what they're called anymore, but I think you get the idea. You are generating a lot of digital content. And what's so important is that under the open science framework or perspective, you should be able to receive credit for all of these digital objects if somebody wants to cite you on them. And so what we can do is we can create these permanent links, DOIs, which we'll talk about a lot more later, but we can create these permanent links and you can put your code, your analytical code in it. You can put your data in it. And what that gives is it gives you a second resource on top of your traditional publication. I'll assume everyone's publishing, right? You can get credit for publications, and typically people are going to cite your publication for its use of your ideas, and people are going to build on your ideas. But what people can also do, if you share your data in code, maybe under a different DOI or under something related to your publication, now people can say, you know what, I read this really cool paper. I don't want to try and reproduce their work or replicate their work or build on it. But what I want to do is reanalyze their data sets. I have a different question because when they carried out their data collection process, they brought 40 participants in and they did some type of experiment, but they also collected this really neat, maybe dietary data. And you want to do an analysis that relates dietary information to something similar that this original author might have collected. And so you might want to do a reanalysis or an extended analysis. And by releasing that code and data, you are enabling other people to work with those materials. And then all of a sudden, now you have citations for your data set. People are saying, I want to use this really rich data set that you went through all of this time and energy to collect. And now you're getting additional citations because you are sharing things that you have already done in support of your own publication. And so that is another reason why we want to participate in open science, because you're already creating so much digital content and you should absolutely be receiving credits. You should absolutely be sharing them because you never know why somebody might want to reuse them. Another issue with the way that things are currently done now is the file drawer problem. And the file drawer problem is this issue that where if your work isn't novel or you found something really cool for experiments that are driven by hypothesis testing, if you don't get that p-value less than 0.05 or 0.001, depending on the field you're working at, the analysis, a lot of considerations there. But if you do not get something that's considered to be statistically significant, then maybe you never publish it, and maybe you say, hey, at that experiment, that was a waste of time. I'm not going to tell anyone I did that, and I'm just going to move on to the next thing. And so I want to present just 3 points of premise and a conclusion for you. So hear me out on this. 1, most academic work is funded by public money, and this creates a pressure to demonstrate value. 2, there is merit in publishing novel studies in high-impact journals, which often prioritize positive or novel findings. And what's important here is that This is something that's deeply embedded into our culture. The reason that there's merit in publishing novel studies in high-impact journals is because it looks really good when you go up for tenure, or it looks really good when you're going to find a job. Typically, these hiring committees are looking for how many Nature publications do you have? How many high-impact journal publications does this individual have? Because that's a sign of their academic merit. When in fact, I don't think it should be as weighted as heavily as it is today, but we'll get into that in a moment. Finally, academia is incredibly competitive, and this incentivizes researchers to focus on publishable results. Therefore, studies that don't work are less likely to be published and may even reflect poorly on the authors. And I will also say that you're often more rewarded if you chase that novel thing that might not work but could be something really cool. You're rewarded for engaging in this high risk, potentially high reward behavior. And what we want to do with open science is not just say, well, you need to change how you work, but we also need to change the deeper culture within scientific or academic research. And so what this might look like is, I'm going to revise our file drawer problem here. All right. Most academic work is funded by public money, creating pressure to demonstrate value. I think that will always be true. I can't think of another way to spin that, because that is just the reality of the world we live in. If the general public thinks you are wasting their taxpayer dollars, then their research might not get funding, or as much funding as you would hope for. But in point 2, there is merit in publishing novel studies in high-impact journals, which often prioritize positive or novel findings. But in fact, I would say that there is also merit in reproductions and replications that builds confidence in our knowledge. Just because you didn't find something statistically significant or novel or interesting does not mean that your work never should see the light of day. In fact, I would say if you don't find something that's insightful or something interesting in a study that you do, you should absolutely find an outlet to publish or share that work, because you never know who's going to come across or find that work and say, oh, you know what, I had the same question and now I won't conduct my study in the exact same manner. In fact, I might learn something about what does not moderate or regulate some relationship of interest here. And so what we need to do is not just value these novel findings, but we should also value reproductions and replications. And I will say, as an individual, I do value these, but we need to also convince individuals who sit on hiring committees that these types of studies are worthwhile. And if somebody has a replication or reproduction of another author as part of their CV, then they absolutely deserve to be considered for their work, because they are showing an academic rigor and a thoroughness or a thoughtfulness in their work, such that if they are skeptical about something, they are really going to tear it apart or really dive into it until they know without a doubt whether something is likely to be true or likely not to be true. On to our third point. Academia is incredibly competitive, and this incentivizes researchers to focus on publishable results. And my spin on it is that, well, yes, science should be competitive to an extent, right? Because we want to use this competition in order to drive research findings. But this also is a slightly double-edged sword, because this high competitiveness can drive researchers to do things that are questionable or unethical, or even lie, in order to receive academic merit. And so what I would spin this to is that science should be collaborative, because more often than not, it has a shared goal. Even those research groups that don't agree with the way that you do things or don't agree with the concepts that you base your work on, you are all actually working towards a shared goal, and that is uncovering some truth. And so I'll say that all work that's thoughtfully carried out should be indexed as public knowledge, which then goes back to support premise 2. And finally, we come to our conclusion, right? Studies that don't work are less likely to be published and reflect poorly on authors. But I would spin this into, studies that don't work are informative and can save repeated effort within a given field, thus saving both time and taxpayer money. And so the file drawer problem should not be a problem. We should be sharing things that don't work, right? As I think Thomas Edison writes, 1,000 ways to not make a light bulb or something of that nature. But I think you get the idea of what the file drawer problem is and why open science can help solve it and why we also need this broader culture shift. And in fact, to support this idea, we can take this figure here. This was published in 2011 from a paper titled Retracted Science and the Retraction Index. This was a group of researchers, or I should say a singular researcher, two of them, who went and created something that they called the Retraction Index. And this was, they took publications from each journal, and through various factors, they created this metric where they could, predict the probability of articles being retracted and then grade them on this kind of continuous scale of 1 to 4 that you see here on the x-axis. And then what they did was they took each of those journals and they plotted, their retraction, their evaluated retraction index against their impact factor. And the general trend that you end up seeing is that journals who have higher impact factors also have a higher retraction index. This typically does mean that these journals are more likely to undergo retractions. And you can think, retractions are not really what we want to see in science. Now, there are going to be many different reasons for retractions, but one of the most powerful reasons for retractions that you'll see is that the authors did something unethical, that maybe they made something up, maybe they used a methodology that's not many other researchers in the field agreed on because they were chasing that really novel, that really cool thing, all in the hopes of being able to publish in these high impact factor journals. And this leads us to a high selection bias, where these high impact journals, sure, they publish things that are really cool, but researchers are bending over backwards. They're doing things they wouldn't normally do in order to be able to publish in these types of journals. And that is one possible explanation for the high retraction index. It is not necessarily the truth because we can only really provide some speculation without a much more thorough analysis, but I did want to share with you that some of these journals do have higher retraction rates than other journals, and typically we can explain some of this by just looking at their impact factor and how prestigious they are. And so that brings us to all of the points I wanted to share with you about why we do open science in the first place. Remember, first and foremost, you want to be able to support your own arguments, and you don't want to do so by waving your hands and talking past points. And so what we do in open science is we share the data and the materials that other people need in order to critique, criticize, or investigate our claims. We also want to fix or solve the reproducibility crisis. And while this isn't going to be an end-all be-all or the perfect solution, it is something that will help us do better tomorrow than we did yesterday. And so by being forthwith with our code and our data, we can help ensure that at least our work reproduces and we can start resolving this reproducibility crisis one study at a time. Also remember that research is not just about you. It involves many other parties. And so we want to be, when we are involving other parties or other groups, we want to be transparent in that communication so that they can make the best justifications, or I should say the best decisions possible, and justify that based on hard evidence, not speculation within a paper or not an abbreviated version of how I analyzed my data or how I collected my data. Additionally, you also should be receiving credit for the work that you're already doing. As we talked about, there are many other things in addition to the paper that you publish that people will want to reuse and cite. And so do make sure that you're sharing these things so that you can start receiving credit and getting a higher citation count, because that is a form of currency in today's day and age of performing science. And so the more citations you have, the more valuable you will be to a given organization, or the more valuable you will appear on a job search. And finally, right, our work does not belong in the file drawer. This is a big problem in today's academic model because of how we value work. And so do make sure that you share everything that you can. All of the work that you have thoughtfully done and fully thought through should be shared because that could be valuable to somebody in the future. And finally, I will say this: open science requires a cultural shift in academia. And so what this means is it's not just about learning a new tool or learning a new skill. We need to change the way that we think about things. And importantly, we need to change the way that others think about how research should be done. And by doing this, once we have convinced enough people that this is important, I promise you, at some point, the money, the incentives will follow. And so what I wanted to do today with you for this first question of why do we do open science is really convince you that this is something that is important to be done, and it's important to convince others to do. And once we are all on board that this is important, we need to figure out how to introduce more incentive to do it. And typically that's going to be in the form of, if you include an open science component in your next research proposal, I will award you an additional X amount of dollars, thus making it more likely that people will embark on open science journeys because they can receive more funding for it by being transparent and embarking and taking on some of this additional work. But with that all being said, let's go ahead and take a short tea break. After our tea break, when we return in just about 10 minutes, we're going to ask the question, well, what does open science look like? Here, we're going to talk about what it actually means to participate in open science, and we're even going to see a couple of tools that I could not wait to tell you about. I know we have a section on tools later, but there are some things that we simply cannot move forward with talking about unless I show you how to use it. So we're going to talk about an open science framework, and we're going to talk about a couple of tools and a couple of approaches and concepts that are important to abiding by this open science framework. But like I said, we're going to go ahead and take a brief 10-minute tea break so that you all have time to stretch your legs, grab some tea, grab some coffee, and I'll see you all in 10 minutes. All right, everyone, that brings us back from our very first tea break. Before we went on our tea break, we were just about to start talking about what does open science look like, and we're going to discuss our use, make, and share framework in order for you to help organize, right, how to do open science. As I mentioned, open science broadly looks like this framework here. In 3 phases, we have use, make, and share, where the whole idea is if you want to use existing ideas or results, data, code, or tools, then you're going to want to be able to find and verify that you can use those things if they exist. If something that you're looking for does not exist, say it's a data set, a tool, a set of results, then you're going to want to make something. And this might mean that you're going to conduct a study, you're going to collect data, you're going to create a tool, you're going to create an open source software tool. And as part of all this, maybe you'll create some type of management plans, you'll write some type of proposals, maybe you'll try and get funding, you're going to create something. And then finally, we have share. This means that once you make something, you should absolutely share it so that other people, and we come full circle here, so that other people can use it. And so, of course, when we share things, there's a lot that we need to keep in mind, whether things can be shared, as well as where we can share them, how to make sure that you receive credit for it through a license, and how to make sure that's not being misused through a license, how you can make sure that we can always find this thing that has been created through some type of digital persistent identifier, such as an ORC ID or a DOI, and then finally, right, how do other people truly cite this? And so there's a lot of consideration that goes into this use, make, and share framework, so we're going to talk about some of the broad questions. When you use something, I said that there are 2 primary purposes for using, or 2 primary sub-processes here for using something. The first thing we want to be able to do is to search for existing ideas, tools, and data. Once we are able to find something through some type of search methodology, then we want to verify that we can use them. All right, so it's a 2-step process here. And if you want to be able to find ideas and results, maybe you'll use something like Google Scholar or one of the many other publication search engines out there. If you want to be able to find data, maybe you're going to use something like Zenodo, Harvard Dataverse, Kaggle, Google Dataset Search, or others. If you want to be able to find a software tool, maybe you'll use Google, maybe you'll use GitHub Search, which I think is an underrated tool. And then to verify that you can use something, you're going to want to be able to thoroughly investigate the metadata related to that thing. And importantly, you're going to want to be able to ensure that the thing you want to use has a license that permits you to be able to use them. So you want to ensure a usable license and that the resource is citable. Those are 2 things that we need to be able to verify in order for us to use an existing product, dataset, code, so on and so forth. Then in our next phase, we have make. If we want to make something, we first should verify that nothing the exact same exists. Don't reinvent the wheel. Remember that science isn't just about recreating things that already exist. It is about typically, right, pushing the boundaries of our knowledge. Now, I will say that if you want to make something and that's a replication, then you're absolutely justified in doing that, right? Because there's some type of question or probability that the truth that a previous study had found is not correct, and so you want to investigate that further. But when it comes to things like software tools or data sets, then we do not need to make these things again if they already exist. In fact, for software tools, you may even be able to improve them by contributing to them. If you make something and once you verify that nothing the exact same exists, as well as all of the concerns around that, you're going to want to plan for openness. And what this means is that you want to be able to take ideas, data, or software tools that you have made, and you want to make sure that you're going to develop or create these things in a transparent way. And so when it comes to making ideas or results, maybe to be transparent with this whole process, we're going to use pre-registration. We're going to pre-register the study. And then we have, of course, our study execution. And maybe as part of that, we're going to want to share data while our study is still ongoing. If we want to make data specifically, well, we're probably going to need to create, as part of our proposal, an Open Science Data Management Plan, an OSDMP for short, or just a DMP for the shortest version. But this is something that we're going to want to do if we are planning to be transparent, because we want to understand and acknowledge that as part of my research process, I'm going to be creating a plethora of digital objects. And you want to be forthwith and say, this is how I'm going to take care, archive, organize all of these digital contents or digital objects. If you're going to make a software tool, then I would highly, highly, highly ask that you prioritize interoperability, making sure that it doesn't just work, your tool doesn't just work on one type of computer, or in the worst case, only your computer and nobody else can use it or run it. And you should also focus on collaboration. And so this might be something that you use some type of code repository service to carry out. Finally, we talk about share. And when you share, you want to be able to enable others to reuse your work, and you want to tell people about it. This is incredibly important because remember that sharing is not just about putting something on like a publicly visible equivalent of Google Drive, right? Sharing is about putting those things in a publicly accessible place that's free for access, and then also telling people it is there. And I find that the self-promotion portion of research is often overlooked. And I will say this as part of sharing is that remember, your null or your quote uninteresting results are still results, and you should absolutely be using them. And I should say you should still be publishing with them through some sort of service, whether that's a self-archive or going through a standard peer-review journal process. Now, what I will say is that if you want to enable others to reuse your work, if you want to enable them to reuse your idea or results, maybe you're going to publish that set of results on a preprint server, which is guaranteed, more often than not, right, to be free and accessible, which is a great thing. Or maybe you're going to want to publish open access. And this is something I would highly recommend because open access is our stamp of approval, or a stamp that says anybody can access this given digital resource, or typically this publication, for free. And that's a big deal because I know that many of us have probably come across some article that's going to be very important to our work, right? You're often, as you do your literature search for a given study that you want to embark on, you're going to find something that says, I've done a similar study and here's all the things I learned from it, and you can't access that article. And it's so frustrating because I don't know a single person who actually wants to pay, I think like $20 or whatever it is to access a given article through a paid journal publication or paid journal subscription. So you want to enable others to reuse your ideas and your results, then you should publish open access, and that guarantees that it is free for access in all time. And then of course you want to share the relevant data or code. If you want to enable others to reuse your data, then you should absolutely search for some type of data archive repository. And I would even encourage you to try and index that data on some publicly searchable forum. Oftentimes, archive repositories won't have the best search engine, and so you may want to investigate other mechanisms to make your work more findable. Finally, if you want to enable others to reuse your software tools, you should absolutely host it on some publicly visible code repository. I've listed GitHub here, but there's Bitbucket, there's GitLab, there's all these other code repository services that let you host your code for free. I'll build on this, and I also will say that if you truly want to enable others to reuse or to cite your work, you should also have your code on some type of archive repository, similar to what you would put your data in. And so we have tools like Zenodo. Now, I've mentioned a lot of tools in these last couple of slides, and so we're going to start talking about those tools. I'm going to break these into two parts. There's going to be tools that we could not live without for the Use, Make, Share framework, and then tools that kind of further enable it. And so we'll see this in two parts here. Now, do remember that when you embark on the Use, Make, or Share framework, no matter what you do, you should be fair and care. Now, these acronyms that I'm about to share with you are typically posited in terms of data, right? Fair data and care data. But I will say that fair is much more broad than just data. It is about sharing any digital artifact. And so what we'll do here with our FAIR principles is we have our FAIR, that stands for findable, accessible, interoperable, and reusable. And so if I want to share an idea or a set of results, right, a publication, if I want to share data, if I want to share code, I should absolutely ensure that these things are findable, right? There is a big difference between me publishing, right, or me going through a publisher, right, to share a PDF, because at the end of the day, that's what your publication is. It's a PDF that's shared online. Me going through a journal who publishes and shares updates with all of its subscribers, as well as having a very enhanced or a very nice search feature, such that anyone who's searching on that journal can find my paper. They're also typically registered with things like Google Scholar, so these results will pop up as part of a broader search engine. Journals have incredibly high findability. So there's a difference between going through a journal and getting all of those additional support for, I'll say for free, but it's not obviously for free because you pay the journal, but you get all of those added in. But you can also think there's a difference between that and me taking a PDF, right, an article that I wrote that I could submit for publication and just sharing it on a personal website that I own. Because you can think, nobody really visits my personal website. Maybe like 5 people a month will visit my personal website versus the thousands or the hundreds of thousands of researchers that will come across a journal if it were shared in something indexed like Google Scholar or a publication journal. Then it needs to be accessible. So just because you share something, whether that's a set of results, data, or code, and people can find it, is not enough. What this means is if you come across a data set that I have shared and you click on a link that says, download data, and then as soon as you click on that link, there's no download, and instead it redirects you to a brand new web page that says, to download this data, subscribe or pay $20, right? And you're thinking, I was so close. I found something that I really wanted to use, but $20, I'm not paying $20. Or an academic partnership, my institution is not a partner with this publisher or with this resource. And so just because I can find it does not mean I can access it. And so we want to make sure all the things that we share are both findable and accessible. Interoperable has a couple of different meanings depending on the context in which it is applied. Typically, right, when we talk about sharing ideas or results, interoperable is going to relate to our use of terminology. And so what this means is that I've told you that I have a background in psychology. I used to do neuroimaging studies using an MRI or fMRI. And you can think that if I took this acronym, fMRI, which stands for Functional Magnetic Resonance Imaging, it's kind of like taking a video of brain activity over time. If I took that acronym and I said, in my next publication, I'm not going to use the acronym fMRI. I'm going to say XYZMF. And why did I decide to change that? Absolutely no reason. I just wanted to make up a new acronym so people will start using it, and I hope it catches on, kind of like fetch. But what this means is that anybody who comes across this article is going to read it and they're going to say, what is XYZMF? Did this person just make something up? I have no idea what they are trying to say. And so when it comes to sharing results or ideas, interoperability typically means are you using the vernacular that everyone else in your field uses? You can also think there's an interoperability layer for both code and data that is a little bit different than just use of terminology. For your code and data, it typically relates to, are you using programming languages that are understandable or free for individuals to use? Does it work not just on a Windows computer, but also on a Mac or a Linux that's specifically for code? And for data, are they using a data format that is non-proprietary, meaning we have an understanding of what this data structure should look like? Or are they using something that I can't make sense of? I don't know how to open this data set. I don't know how to work with it, and thus leading to a lack of interoperability. And so the I for interoperable takes on a couple of different meanings, but typically at the broadest sense, it's if I can find it and access it, can I make sense of it? Can I get it to work? And then finally, we have our R for reusable. If it exists, can you manipulate it? Can you reuse it in the fashion in which you want it to be used? So that is our FAIR principles. They relate, in my opinion, to all facets of open science, not just our results, or not just our data, I should say, but also to results as well as code. Now, we also have the CARE principles, and this is one of those very interesting acronyms. And the reason I think it's so interesting, because it's the first time that we have stopped and thought about, yes, we should share everything. But there's always going to be a stipulation. There's always going to be some condition that says, you know what, maybe we shouldn't share this particular piece of data. And you can think, if I work with humans, as I have, right, as a psychologist or a psychological researcher, then I collect data on people. And one thing, if I collect, first names, last names, heights, weights, and social security numbers, and I say, you know what, here's my data set. It has everyone's first name, last name, height, weight, social security number, and age, date of birth. Here you go. I was told to share this. This is open science after all. You're probably going to say, wait a minute. Should we be sharing all of that personally identifiable information? In fact, if you live in the United States, and I'm sure many other countries have policies like this, you're legally not allowed to share health information, hence our HIPAA Act in the US. But what I will say is that it's important. Every time you think, I should share this, right? I should share this data I collected. I should share this code that I've written. You have to ask, should I share it? And the first person you should ask this question to, if you want to share something, is going to be some form of supervisory body at your institution. So if you want to get started on sharing something, you want to make sure that you are going to be abiding by your institutional policies and regulations that exist. And this is paramount, because they are going to typically have the most cut and dry answer for you as to whether or not you should be sharing something, or they can provide you guidance on, if you do have, personally identifiable information, what fields need to be absolutely eliminated before sharing and what fields can be included when you share, because we can do this process of typically anonymization, where we remove some of the relevant or some of the irrelevant details and just focus on, subject ID 0193. As opposed to a first name, last name, social security. And then you can provide maybe their responses that they made to some type of questionnaire that you provided them. And so in terms of working with people, our CARE principles are all focused on that. In fact, our CARE principles here are purely for data, and it's for data when you're working with populations of people. And so the CARE principles stand for collective benefit, the authority to control, responsibility, and ethics. And you want to make sure that if you are collecting data on a population of individuals, that data set can be used, or is going to be used, to serve their collective benefit, meaning it will help promote their health and well-being overall. Additionally, you also have to realize, especially when you are working with people, that they have the authority to control that data. Do you own the data you collect? More often, especially if you're working with people, you do not have sole ownership over that. If they provided to you, right, their names, information, and other things, they have the absolute right to revoke that information and have that information not be shared. So make sure that the groups that you're working with have the authority to control their data before you share it. And then finally, we have responsibility and ethics, both of which promote the underlying messages here in the CARE principles, and that is, if you are working with people, you should serve them in a manner where you are going to provide their benefits. You should conduct yourself in a responsible manner, and you should always consider the ethics of the work that you are doing, because this will give you some guidance as to maybe I shouldn't share this portion of information. And in fact, going beyond some human subjects testing, right, and personally identifiable information or healthcare information, you can also think, well, if I work for the government and I design maybe weapons that are used by the military, do physics research, then maybe I'm going to be limited in what I can talk about or what I can share online, because my government's going to limit me, since it's a national security interest in this point. And so there are many reasons that we may not want to actually share things. And so our CARE principles are going to be here to serve as a reminder for all of my people who work with humans about these specific principles. But for all of my friends who do not work with human subjects and think, well, CARE principles don't apply to me, use this as a reminder that there's going to be some limitation as to what you should share. And you should always be thinking about, how could this be misused? How might this hurt a group or people or maybe animals or things like that? Because there may be some pieces of information that do not need to be publicly accessible, and they don't change, right, how one might interpret your results. So always think about what you should not share, in addition to being empowered to share. And so let's talk about the first of our tools. Now, from our use framework, we had our data and publication search portals. I listed just a couple on the previous slide. We had, I believe, Kaggle, Google Dataset Search. In addition, we have Wikidata, Open Data Network. These are all examples that I just listed of generic search portals. And what this means is you can find any data set through them of any discipline, hopefully. We also have domain-specific search portals, meaning if I want to find something specific about Earth data, then I should probably use NASA's Earth Data Search Portal. Or if I want to find something about climate data or something about physics, maybe I'll use the NOAA Climate Data Online database or the CERN for particle physics in specific. There's also national and international data search portals. So if I want to do some analysis or research or work on maybe U.S. Census information, so broad population questions, then I could use U.S. federal data or the EU data portal or something from the WHO. Many governments and nonprofits provide search portals for you to use data freely or with some paid caveat on top of it. So these are three types of search portals that we can use to find data. I want to quickly take you through one of these search portals, such that we'll take a look at Google's datasetsearch.google.com. I'll of course share that link in the chat with you all as well. But it's so easy to use, it's as easy to use as Google. So if I want to find something about maybe rainfall and find some weather-related data set, I can absolutely just type rainfall into the search engine here, and it starts providing me with different sources of data. Now, investigating these sources of data is very important. We're going to talk about metadata in a little bit and the questions that your metadata should answer. But you can absolutely think, if I find a data set that does not have a license, I can't use it, right? I can't determine if I can use it, therefore I can't use it. Or if I find a data set that's, very sparse in maybe its methodology, it doesn't say anything about how it was collected, then I can't trust this as a data set. So we'll talk a lot about relevant metadata that you are going to want to include when you share your own data sets, such that anyone else can come over and reuse your data set with confidence. But you can see here that our Google dataset search gives you a couple of pieces of metadata, right? Importantly, it tells you where, right, some of these data sets live or originated from. It's going to give you the last date of update for that data set. It's going to give you who authored it, who created it, and then hopefully they're going to tell you about the span of time that the data exists on, and importantly, how it was collected, or if any pre-processing or any steps have been done to these data since their original collection. You can see here this weather station data were interpolated using this specific methodology. I'll increase the font size a little bit here just so you can see that a little bit more clearly. But you get the idea that you want to be able to describe any transformations or manipulations that have been done to your data. And so Google Dataset Search is a fairly good one to use because oftentimes the metadata is nice and descripts and fully thought through. But I will say some of these other search engines, like if you've ever used Kaggle, it's good if you want to do, a quick like machine learning competition, but I wouldn't say it's necessarily where you're going to go find a data set for an academic publication. So if I search rainfall in here, we're going to just find, rainfall predictions, 7 popular models, and I can even look for a specific size of data set or specific file formats here, but a lot of them are going to be more teaching oriented, and they're not going to have a thorough evidence provided as to where these data sets came from or what's been done to them. They're typically going to focus more on other facets or other features about the data set. So I would definitely recommend, right, using things, using maybe Google's dataset search, or honestly, your best case is going to probably to use something that's discipline specific, or use a government provided data set as well. Now, there is one other avenue to finding a data set, right? We have search portals that we just talked about, but there's also what I like to call the rabbit hole. And what the rabbit hole is when you are reading papers, when you're reading articles, you're going to come across data sets that they collected and that they used or authors used in the articles that you're reading. And if they have shared these data for reuse, then you can absolutely make better use of them. And so, sure, you can use a search portal and you can hopefully find something that's going to be relevant to your work. But as part of your literature review, I would also encourage you to track what data sets are free and accessible that other people have used that you can then use in your own work or in your next study. In addition to data search portals, we also have publication search portals. And I suspect many of us will be familiar with these, right? This is for our generic publication search portals. We have Google Scholar, we have Open Knowledge Map, which I absolutely love, and I'll show you in just a minute here. And then for our domain-specific search portals, we have publication search portals like NASA PubSpace or Europe PMC for life sciences or PubMed for biomedical literature. These are all they will typically be journal search engines, but sometimes they're going to be beyond a specific journal, but they're all going to be domain specific, meaning within a singular field. So whether that's biomedical literature or that's life sciences or physics or anything else, that's going to be our domain specific search engines or search portals. Now, one thing I will say, for those who have not used Open Knowledge Map, I think it is such a fun tool, such a good tool to use, because it takes your typical literature search and it starts organizing it or curating it for you. It gives you a very good jumping off point for your next search and your next search, and it's going to help you find some of those key relevant papers or articles very quickly. And so if you're ever taking kind of the first dive into a field or first dive into, right, a sub field within your discipline, then Open Knowledge Maps is actually a very fun tool to use. We'll take a look at the output here as it comes up, but I just searched the term neuroscience, right? And maybe I'm just curious, well, what are popular things to study within neuroscience, or maybe what are some broad categories within neuroscience. And you can see that Open Knowledge Maps has created a nice graphical user interface for me to explore different aggregations or clusterings of topics within neuroscience here. And so if I wanted to get interested in maybe doing educational neuroscience, well, then I can take a look at these papers. And so I can click into this circle here. It opens up all these papers and citations. It even lists which ones are posited for open access, meaning I know I can access them for free, which is a great thing. But this is just a tool that helps you enhance your search for your next literature project. You can actually, if you create an account here, you should be able to create and, of course, save these types of searches so that others can reuse them as well. Or you can say, here's my knowledge map for my upcoming project. Now, a brief aside, since we talked about finding things online. I've mentioned this in passing before, but I really wanted to focus on it, and that is licenses. Data use and data licenses. There's also going to be software licenses. There's also going to be creative licenses, which are all slightly different from one another, but the broad gist is this. Before using data, software, or anything, you should absolutely read and understand its license. I promise you the text on these licenses, although it's written in all capital letters and it looks a little bit daunting, it is not as deep as you might think or not as confusing as you might think. But a couple of key points here. If you find something and it does not have a license, you cannot use it. Remember that a license is a legal document that tells people what they can and cannot do with a given digital object, in this case, a data set. Without a good understanding of what that license allows, it will actually open you up to possibly copyright infringement or other intellectual property issues. And remember, no license means no use. So it's good to ensure that a license exists and that you understand what it means or what it implicates. They'll often have clauses about how you can reuse it or to what capacity, or maybe you can reuse it for an academic purpose, but you can't go ahead and base a company off this data set or code or whatever it is that's being shared. And finally, there's going to be some edge cases with licenses. And this is why I always provide the guidance to get in touch with either a legal body or some type of supervisory body at your institution in which you work if you want to use things. Typically, if you work at a university, your library will have the answer to many of these questions as they apply to your institution. There is some one-size-fits-all information I can provide to you, but we can't get into all of the nuance. And so you can see some of the corner cases that's written down here, but I will say, remember, no license means you can't use it. A license is simply a legal document that tells you what you can and cannot do with it and how you need to go about using it if there are those types of stipulations that exist. And before you use data, please read and understand its license. But let's get back to our Use, Make, Share framework, talking about some of the tools that help support this. Now, we've seen our search engines, right? If we want to use something, right? We have data and publication search engines. But if you want to make something like a study or a set of results or an idea, I can't strongly recommend this enough. You should pre-register your next study. Now, some fields, pre-registration doesn't make a ton of sense to do, but I will say for most fields, or I will say for any field where you're doing hypothesis testing, you should absolutely pre-register it. And if you want pre-registration summarized in a single quote, I have it here. This is from the Center for Open Science or the Open Science Foundation. And it reads this. All pre-registration is you're simply specifying your research plan in advance of your study and you're submitting it to a publicly visible or some type of indexable registry. That's it. And this involves much more work than just that single quote will say, but it's work you're already going to do anyways. And what pre-registration looks like is if I have an idea for a study, at the time of my idea or writing up a proposal, you know what I can come up with? I can come up with why I'm doing this study. That's the introduction to my paper, to the publication I'm going to write later. But I can write up an introduction without actually having collected any data. And in fact, I should absolutely write up an introduction without having collected any data, lest I want to have some hindsight bias. So, to pre-register something, write up your introduction. Say, this is why I'm doing this study. You can also say, well, I'm planning to analyze the data in this particular fashion. Here's my methodology for my data analysis. Here's my methodology for data collection. Here's my methodology for X, Y, and Z. And so you can actually write most of your research paper before having even collected data from a single entity. And this is what pre-registration is all about. It's about saying, these are all of the things that I am intending to do as of right now before I go ahead and actually collect or analyze or whatever phase I'm at in my research process. And the reason that we do this is without knowing it, and I'm sure many of us are aware of this idea, but without knowing it, right? Many papers that we write or that we have read have a strong type of hindsight bias where researchers predict A, they observe B, and they're wondering, where did B come from? This is so odd or interesting. And then they rewrite the introduction to say, you know what, we suspected B all along. And that's not how the research actually happened. That's not how things actually went. And wouldn't you want to know if somebody found something that they completely did not expect? Wouldn't you want them to be transparent with that fact as opposed to saying, well, we knew it all along? Because you can think that if I found something unexpected and I wanted to market it as novel, cool, or we should have seen this coming, then I'm going to be highly cherry picking some studies to go back through and say, you know what, this is why this idea is supported. Now, it's okay to leave this type of reasoning in the conclusion, but you should be forthcoming and say, you know, I was predicting to do something else. And in fact, this is just one problem that pre-registration helps us avoid in the broader publication space. In fact, pre-registration will help us combat p-hacking or data dredging. For my friends who don't use statistics in their work, p-hacking is the idea in these experiments where statistical results in this small probability value called a p-value is pivotal in today's publishing space. Being able to publish means you have statistically significant results, unfortunately, right? And that's something we want to change. But p-hacking is this idea that if you're doing some type of hypothesis testing and your results are going to be predicated or investigated or valued based on getting a statistically significant result, and you do not get one. Well, you know what you can do is if you have three groups of people and you looked at all of the, or three groups of subjects and you looked at all of those groups, you can then divide those three groups into more groups. What you're doing is you are underpowering your study. And when it comes to performing a statistical test, studies that are underpowered, typically meaning, right, that have small sample sizes, you're going to actually increase the rate of detecting a false positive, meaning you're increasing the likelihood that you're going to be below your p-value threshold for something statistically significant. And all you're doing, you're not changing, right, the data. You're simply enhancing how they're grouped, or you're changing things that maybe people won't notice. And think about this. If I collect data on 100 participants, and then at the time of publication, I say, or at the time of analysis, I find out, these results aren't statistically significant. But you know what? If I take 30 of those participants and I say these need to be removed for whatever reason, and I'll just make up a reason, and then I now have a data set of 70 subjects. Now when I do my statistical analysis, there's something interesting. There's something statistically significant. And then when I go to write it up, I just say I collected data on 70 participants, or maybe a little bit more realistic, I collected data on 100, but I only analyzed these 70 because here's my justifiable reason, I just made it up. That's what we want to avoid. And we can avoid that with pre-registration because I can say, I'm intending to collect data on 100 participants. From these participants, I'm going to exclude their data if they meet these a priori created thresholds or a priori created conditions. I'm not going to make something up after the fact just because that result supports, my ability to get published or supports my idea that something should be statistically significant. Pre-registration will also help us avoid harking. This is an acronym for hypothesizing after results are known. This was the issue I was getting at earlier where I said, well, you find something maybe you didn't predict or was unexpected, or you collect a lot of data and you have a primary analysis and the primary analysis doesn't work. And then you just look at the data and you say, what correlates with something else? And then you publish on that correlation, and you publish on that correlation as if the study was all about that correlation and if you knew this was going to happen the whole time. That's not how the science actually went down. You're misleading or lying. You're creating that tight, nice, buttoned up article to share, but that's not really what happened. And wouldn't you want to know the truth if you're reading this article? Absolutely. So pre-registration helps us combat that. It also helps combat things like publication bias and selective reporting. So these are all things that pre-registration can help us do. In addition, pre-registration is going to help us be more organized because I know probably all of us like to collect all of our data, do our analysis, and then in about 3 weeks of time, write up as quickly as possible some type of semblance of our rough draft of this article that we want to publish. And if you do this in advance, you're going to save yourself a little bit of time and headache, and you're also being more transparent and more honest with your work. And I will say, pre-registration is so easy to do. There's so many websites and tools that you can use to it. I'll take a moment to talk about or to show you the Open Science Foundation, osf.io/prereg, but you can also use other services like As Predicted. So let's go ahead and take a quick peek at how we can pre-register a study. Now I've gone to that link that you saw on your slide. I'll paste it in the chat for you all as well. And that was osf.io/prereg, P-R-E-R-E-G. And once you do that, you'll need to create an account. You create an account and it brings you to this page. And all I have done is I've clicked, yes, I would like to create a new pre-registration. And it brings you to this this portal here where it takes you in a step-by-step guide on how to create a pre-registered or index a pre-registration. And so for our first step, do you have content for registration in an existing Open Science Foundation project? Now, Open Science Foundation doesn't just do pre-registrations, they also do other things, but they can help you manage your project end to end from coming up with a collection through collecting data and through publication. And so that's what it's asking me here. Do I have content to pre-register in an existing OSF project? Now, I don't have any Open Science Foundation projects currently open, and so I'll say no. And then finally, it asked me what type of pre-registration would I like to create. So you can see there's a couple of different standards here, and it's not horribly important what standard or what series of questions you adhere to, so long as you are pre-registering something. In this case, I'm just going to use the default here, the Open Science Foundation pre-registration form. And I can create a draft here. Now, this is going to ask me all of those questions that I should already know the answer to or should already be able to speak to. In fact, I should be able to say, well, what's going to be the title of this paper? Maybe you don't, I know a lot of people who like to come up with titles after the fact because they like to make them flashy revolving around the finding that they got because you don't know if something's going to work out. But you can come up with a title here. You come up with a description. You can add contributors. So if I want to add another person who's going to contribute with me, I can add them, and I can also assign them permissions. This does mean that you can collaborate with other people on a pre-registration. We can all share this form. We can all make changes and add comments to it. And so I can add other people. I can change permissions. I can add a license. And we've talked briefly about licenses. We'll go a little bit more in depth when we get to software licenses, but they have a couple of selections here that you can make. Broadly speaking, an MIT license is going to be more for things like software because it has specific clauses about code use and code reuse. Then we'll see that there are the Creative Commons licenses, which are also very common to use. They don't have anything about code use or code reuse, so typically these are going to be used for data or anything creative, right? Anything artistic like slide decks or logos. But with the Creative Commons, you can add additional attributions to them, like this work cannot be used for commercial purposes and you cannot create derivations of this work, or the share alike clause, meaning if you reuse or redistribute this work, which I'm giving you permission to reuse and redistribute it, you have to use the same or similar, you have to use the same license that I published or I shared under here. So there's a lot of different licenses here, and I'll give you some resources to go more in depth with them as you see fit, but the important thing is that you share a license for the reasons that we've talked about earlier. You can also select what specific discipline your study will be in and add a couple of tags. Now, tags are important for the findability of our work. As we'll see later, metadata is crucial to the FAIR principles, and adding tags is something that can help people come across your work or find your work. After you fill out the metadata, you would click Next, and you would enter the study information here. And so you're going to enter your hypotheses, what you are predicting what you're predicting as part of your study. Then you get into the design plan, and here you fill out how are you going to collect data, how are you going to analyze that data, and so on and so forth. You'll also select what type of study is it? Isn't it experimentally manipulated study? Is it going to be something observational? Is it going to be a meta-analysis or something else? If it's a blinded study, meaning the researchers don't know what group is what, is it going to be a single blind, a double blind, so on and so forth? And then what is the actual process that you are going to undergo to collect data or to embark upon your study? And so you should write about this in very in-depth detail. And then finally, you can attach some additional files here. Once you figure out and write about the design plan, you get into the sampling plan. And so this will be more so about how you go and are pre-registering or collecting observed data. And so this is where you say, I created this pre-registration prior to the collection of any data, or I've been pre-registering prior to accessing the data or prior to the analysis of the formal analysis. Maybe you've already taken a look at it. So you'll have an explanation of data that exists or data that you collect, how you go about collecting it, what software you're going to use, and things like that. Actually, you're going to include a lot of the relevant things that you would include in your Open Science Data Management Plan, something we'll talk about shortly. You'll also discuss any variables, so the experimental or manipulated variables, as well as anything that you're trying to hold constant. You'll talk about your analysis plan as well. So what types of statistical tests are you going to run? What type of pre-processing or how are you treating the data? And then there's, of course, a place for any additional information. And then finally, when all is said and done, you review your pre-registration. And so given that you have a study in mind, these are all things that you should be able to fill out and answer. But honestly, that is all there is to it. This is not doing more work. This is stuff that you're already going to do, and this could be treated kind of as a rough draft of a paper where you can pull portions of this and reuse them in your paper because you've already written about the methodology that led to your data collection. And it's just going to enhance the transparency and honesty in the work that you're doing, and importantly, in the work that you ingest or the work that you read about. So that's what pre-registration is. It is so easy to do. Go to openosf.io/prereg. And of course, I'll share this slide deck with you all, and you can have the link to a step-by-step guide as well. So the next thing I would like to talk about are Open Science Data Management Plans. Now, Open Science Data Management Plans are things that you're going to need to start writing if you haven't already written one, because it is a detailed plan that grant reviewers are increasingly likely to want to see about how you're going to manage all of the digital content that you are creating. And I'm not talking about you own a blog and you're creating digital content, but I'm talking about you're collecting data, and what is that data going to look like? What file formats is it stored in? When are you actually going to share this data? This is open science, so hopefully you're planning to share. Where are you going to share these data? How does this plan actually enable long-term preservation of the data? And who's actually responsible for implementing this data management plan? And so we have these 5 questions: what, when, where, how, and who, all things that you need to be able to answer about the data. And importantly, other people are going to have these questions if they want to reuse your data. So when we talk about the what, we typically refer to what are the file formats that you are storing these data. And so we have a couple of different file formats here on the screen. Some of these might be familiar, like CSV, comma separated values. These are text-based files where you have the ability to open up this file in a program, any simple text editing program. If you're on a Windows, something like Notepad or Notepad++, you can absolutely open this CSV file. You can take a look. It's all just text, so we can read it with our human eyes. But then we also have other things like Parquet files. Now, if you're not familiar, Parquet file, this is not a text-based file, right, where you can just open up in Notepad and read it. This is a binary-based file. And what this means is that you need typically a special program to open up and read it. Now, the reason for this is text-based files, they're not great at storing large volumes of information. In fact, they're not great at storing some metadata associated with those information as well. But text-based file does get an added bonus for its reusability component, because any simple text editing program that every computer pretty much has by default can investigate, open up, or examine the contents of these files. With a Parquet file, you'll need a more specific program that can work with Parquet files, but the trade-off here, the thing that you get, is typically you're going to have a file that's going to be a smaller size. So if memory footprint is something that's concerned, then you might want to lean towards a Parquet file. Additionally, there are going to be the programs that are specialized for working with a binary-based format, such as Parquet, are typically going to be faster than our programs that work with just text-based files like CSV. So there's a memory footprint as well as a speed, but you lose out on a little bit of interoperability. That being said, Parquet files are an open standard. They're publicly discernible, and there's many tools that work with Parquet files, so they're a good choice to use. Parquet files, though, specifically are for tabular data. They're typically for large volumes of tabular data, and they're becoming an increasingly common standard to use. But I will say, large data that you're going to want to store a Parquet file in, I'm not talking like 100 rows. I'm not talking 1,000 rows. I'm talking about once you get to 10,000, 100,000 plus rows of tabular data, then it's time to think about a Parquet file. But if you have data on 200 entities, right, and you have 20 columns or something like that alongside that, or even 100 columns of 200 entities, the CSV file is going to work just fine. It's not going to be too slow. The only added benefit that you get for Parquet are going to be some column-based metadata. Now, those are both examples of tabular data, which I think is the most common, or at least everyone's familiar with, because we've all used Excel, so you've seen tabular data. But we also have other types of data or other data formats like JSON, HDF, NetCDF, ISA, and FITS, which are going to have different uses. But the important thing is not just that they'll have different uses, they're also going to be common in different disciplines. And so if you are working with climate data, you'll probably be familiar with NetCDF, but a psychologist like myself, I don't use NetCDF all the time. And what I want to say is this: use the file formats that are common in your field. And so if nobody in my field stores, volumes of data in a Parquet file, I'm going to lose out on a little bit of interoperability because I'm introducing a new technology that others might not be familiar with. But if the Parquet file is, vastly better and I can justify it, it could be worth it. But if I work with climate data, then I'm probably going to be using NetCDF, right, to read in data from other sources. And so maybe when I share my own data, I should also use that because it's an established common file format. So be aware of the file formats that are used within your field and make sure that you reuse them so that others are familiar with them. We also have the when. Now, the when relates to when are you going to share this data? And we have 4 common categories of sharing. First, we have an advanced sharing. And so an advanced sharing just means that you share data at the time that you collected it or really soon afterwards. Some funding agencies will even require this, or they'll allow what's called a short embargo period. An embargo period just means that I've collected this data, I'm going to share it as soon as I can, but it's in everyone's best interest that I investigate the data to make sure that my machines that were collecting these data were calibrated correctly and make sure there's no artifacts in my data. Maybe I need to make sure that there's nothing identifiable in it if this data relates to people. So I'm going to take a couple of weeks or maybe 2 months after I collect this data to clean it up and make sure it meets all of these criteria that we have agreed upon that it should meet. And if it is not, then I probably shouldn't share this data because it could be misused or misinterpreted. I should also maybe consider intermediate sharing if advanced sharing is an option. This is probably the type of sharing that some of us are already doing. And this just means that you share your data at the time of your publication. And so many publishers already require that you share data. And I hope to see that number go up. I hope to see every publisher require that you share your data at the time of publication, because that's just going to help our reproducibility. We also have minimum sharing, and this just means that you'll share these data at the end of a grant. I will say maybe this is the one to be avoided, especially if you have long multi-year grants, because I have seen people get into a really tight situation where they've collected data over 2 years and then they spend another year and a half analyzing it and writing it up. And then by the time the grant ends, they're thinking, oh, all that data is such a disaster. I did say I was going to share it though, so you know what? I'll just throw everything into a zip file and I'll put it online and I'll never think about it again. And we want to avoid this situation because you're then just sharing your mess online, and that's what you don't want to do. But if you're a very organized individual and you can organize data over the lifespan of 4 years without archiving it, then minimum sharing, as its name suggests, is the least you could do, is share those data that you collected when your grant is up. Now, finally, there is, of course, an option to not share anything at all. Or I will say to maybe click that checkbox that says data available upon request, because we all know that that doesn't really mean anything. But in addition to that, there are many reasons that you should not share data. And we've talked about a few of these already. And so it's up to you to determine when you should share data. And if you're writing a data management plan and you want to do no sharing, you know a couple of the reasons that are going to be justifiable for writing a data management plan and getting it past a review committee. There's also where. Where are you going to put these things? We've seen a couple of general repositories. We will be revisiting these, particularly Zenodo, just because it's an easy example to use, but there are going to be storage places on the internet where we want to put data. And the key feature about these storage or archive services, as they are called, is that they help us guarantee that the things we upload to them do not get deleted. And what that means is if I have a link or a URL that takes you to a specific web page and I share that with you, with most web pages on the internet, right, there's no guarantee that just because that link works today means it will work 5 years from now. And you can, if this link points to a data set that helps you reproduce an analysis that I did, you don't want that link breaking on you. And so archive services like Zenodo, Mendeley Data, Figshare, Dryad, Harvard Dataverse, and many others will help you ensure that you can upload something to them for free and you'll get back a link that is guaranteed. And I'll use that loosely because it's impossible to make a full guarantee, but they will do their absolute best to make sure that that digital object, that resource, does not disappear or break. We also have the who. This was the final question on our data management plan. The who just enumerates who is actually going to be in charge of implementing this data management plan. And when we talk about the who, remember that you need to answer this question for every single phase of data collection all the way through the end of your study. So who is actually going to be creating data or digital objects? Who's going to be collecting it? How is it going to be collected? And once you have collected data, who's going to be in charge of maybe sharing that data with the rest of your lab or with any other collaborators? Who's going to be in charge of tracking, managing, curating the data? Does pre-processing need to be done? Is there going to be some associated metadata, such as this data was collected from instrument number 1, or maybe instrument number 2 was broken that day, so we had to use a backup instrument, therefore its readings might differ from previous readings. These are all valuable questions that we need to answer. We need to know who's going to be in charge of making sure these things are written down and documented. And then, of course, who's going to be in charge for archiving the data? Who's going to actually click the upload button to Zenodo or to a similar service and make sure that these things are archived for long-term storage? And then finally, who's going to go back and make sure that these storage solutions still work a year later, 2 years later, 3 years later, so on and so forth? And although this feels a little excessive, when you are creating digital artifacts, it is important to be able to answer all of these questions. Not just the who, but the what, where, when, and the how as well. And to help you organize all of this information, I want to share with you another tool, and that is dmptool.org. For those who are not familiar, this is the data management plan tool. You can create an account completely for free. And then you'll come here once you sign in, it'll show you your dashboard, and you can click create a plan. Now, this will then take you through another set of guidelines. And you'll have to just fill out these questions one by one. So what research project are you planning to collect data for? I can say, I could make up a title here or make up a research project. So maybe I'll say monitoring. For some reason, I really love rainfall. Even though I studied psychology, rainfall is just on my mind right now. Probably because it's a little bit rainy where I live right now, but monitoring rainfall, or maybe I'll do something, let's change it up. Maybe I'll say, facial recognition advancement. That's my project title here. I want to make facial recognition better so that we can identify people from further away or something of that nature. For today, I'll click that this is a mock project for testing, practicing, or educational purposes, so it's not a real project here. And then you would fill in your institution that you perform research at, or you can check there is no institution, and then you can select the primary funding organization and type it in for a list of suggestions. So if I have the National Institutes of Health, I can fill that here, or I can say, since it's a mock project, there's no funder in this case. And then you can create your plan. This is, again, going to take you, very much like our pre-registration, take you through just a series of step-by-step tools. The thing I love about using DMP tool is that you can get collaborators on board and you can fill this out. Since this is going to be included as part of a proposal, having this be highly collaborative is going to serve your benefit. So you can write an abstract about your project, select a domain, select start and end dates, and then you move on to, well, who am I working with? And you can add collaborators here. You can add them by email, so it's fairly easy to get up and running. And then, of course, you can select their permissions. Then you get into writing the actual plan. And you'll notice that a lot of these questions are going to be similar to the questions we've already talked about. So these are questions about data collection. What data will you collect or create? And how will the data be collected or created? And you should write this thoroughly. On the right-hand side, right, it has guidance that has been provided, right? What, maybe questions you should consider. What type of format and what is the volume of data? Is it 1 gigabyte of data? Is it going to be 10 gigabytes of data? What's your best guess? And you can even have comments. This is part of the collaborative nature. So if I fill in that I'm going to collect, I'm going to monitor people's faces through some tool here, then I can have a collaborator and say, you know what, maybe we can't just monitor people's faces. Maybe we should get them to come in to do a study and provide consent. And they can say, okay, that's a fair thing to add into our data management plan here. So we have all of these questions that we can go through and we can collaborate on them, but you can see you have data collection, you have documentation metadata, ethics and legal compliance, storage and backup, selection and preservation, so on and so forth. And then you get into your research outputs as well as finalizing your upload, but your research outputs are going to just be examples of what you're expecting to create. So a list of your anticipated research outputs here, and then you kind of review just like we would do for pre-registration, and then you can download your plan. You download your plan and then you upload it as a proposal document to the grant that you're writing. And that's how the DMP tool works. It's really just there. You don't need it to write a data management plan, but it's there to help you think through and collaborate on a data management plan. I will also say that on this website, you can find existing data management plans that other people have written and submitted. Not necessarily that they got approved or awarded, but they do exist. So if you need to look at how other people are doing things for some inspiration, you can do that on dmptool.org as well. But taking a quick look at the clock, I see that we are just in time for our next tea break. So what I'll do is I'll go ahead and put 10 minutes on the clock. We'll have time to grab some tea, grab some coffee, stretch your legs, and I'll see you all in just 10 minutes. All right, everyone, welcome back from what will be our final tea break as part of our makeup session. We'll jump right back into where we left off. We just finished talking about data management plans. And remember, this was all embedded within our use, make, and share framework. And data management plans are critical to when you want to make or collect data. And of course, write a proposal for part of that collection or for that study you want to run. So let's talk about our final portion of what it looks like to do open science. And that is going to be open access publishing. We've mentioned this before, but we're going to go into just a little bit more depth now. Publishing open access, as I've shared earlier, means that when you share your materials, or I should say, when you publish your article, right, that publisher is not going to charge anyone else for access to that article. And this is a phenomenal thing. This helps with our FAIR principles. Remember that the A stands for accessibility. And if there is a paywall, it is not accessible, or it is less accessible. And we can do a much better job. And so what I have here on the screen are 3 different routes that you can take to, quote, open access publishing. I will say only 2 of these actually end in open access as it relates to the stamp of open access, but we'll talk about all of them. We have 3 lines, right? We have the gold line, we have the diamond line, and we have the green line. And you can follow each of these lines where they visit and where they stop. And if we start with the gold line here, we can see that we optionally go by a preprint server. And a preprint server is just a place where you can deposit an article for free online. You get a digital persistent identifier, in this case a DOI, in return. And this is a great solution because there is no peer review process, or this is a great thing you can do because there's no peer review process, but it's stamping your idea, your article with your name and a date such that you won't be getting scooped right along the way. So nobody else is going to come in with the same idea before you, hopefully. So preprint server is a great place to drop off a preprint of your work, but then we of course need to go through the formal publication process, and that's peer review and publish in a journal. Now, I have here published in an open access journal since these are routes to open access publishing, and we want to make sure that we publish open access. But you're probably wondering, why are there 2 lines? Why is there a gold line and a diamond line? The reason is for this. The gold line implies that, yes, we can stop by a preprint server, we can go through peer review, but the journals that we are submitting to are going to charge us an additional fee. This is called an article processing charge, or an APC. And they charge us because it costs time and it costs resources for this journal to then host for freely, like for free access on their machines or on their devices. And so that money needs to come from somewhere. If they're not going to charge, right, the viewers of the article money for viewing it, then they're going to charge the person who wants to submit it or to publish it. And unfortunately, sometimes these APCs, the article processing charges, can be quite expensive, upwards to somewhere around $2,000 US, which unfortunately is a lot of money. And this is a barrier to publishing open access, but thankfully, there are things you can do to reduce or source that funding from somewhere so you don't have to pay it out of pocket. The first thing I would do is investigate whatever grant that you're publishing on behalf of, see if you have any indirect expenditures left over, indirect funding left over, because you can actually likely put that towards, right, publishing an open access journal and paying that APC. However, if that is not your case, then what you should really do is probably look for the diamond line. And the diamond line does require a little bit more planning. But the diamond line is the exact same as the gold, but it means one of 2 things. The first thing is that the open access journal that you're going to publish in has some type of relationship or agreement with your institution, where maybe the institution pays this publisher. And that means that any articles coming from this institution will be deposited for open access. So there's no charge to you as a researcher, but your institution already has it covered. Or maybe you've already allocated very explicit funds in your grant proposal, such that you have these funds on hand to pay an APC because you put it into your proposal from the get-go. However, you can also find a number of open access journals who will actually not charge you an APC. So you can always keep an eye out for those as well. And these are great things. They receive funding from an external third party typically, because again, the money has to come from somewhere because they are providing a service, but they don't pass that fee on to you. They get it from an external party. And so we have our gold route, where you pay the APC, the article processing charge, so that they can publish your final version under an open access license. We have the diamond route, right, where I said it's a subset of gold, but the journals don't charge the author because they receive alternative sources of funding, whether that's from a third party, whether that's from your institution. And we also have the green route here, which is just the process of self-archiving and preprints. And so the green route makes a mandatory stop at a preprint server where you drop your article off. You skip the standard peer review and open access publication, and then you simply go and self-archive, meaning you put your code and data right up on some type of archive repository, like Zenodo, as we've talked about recently, but we will go into more depth. So if you are curious about how to find an open access journal, I would highly recommend doaj.org. That is the Directory of Open Access Journals.org. This is a search engine which will find open access journals related to any search terms that you plug in, so that you can find a journal that best suits your work and ensures that your work is not just findable, but also accessible. So that is what open science looks like. Remember, we started with the use, make, and share framework. We also want our open science to be transparent and methodical. And as part of this, right, to be transparent and methodical, we want to pre-register our studies and we want to write effective data management plans. We also want to make sure that we're putting our code and data available for free and for permanent access. And we want to make sure that we get a DOI and that we use an appropriate license. Now, these were parts of the questions that we answered when we talked about our DMP, but we're going to see in much more in depth how to do part 3 just after this. And finally, we want to make sure when we publish, we do so open access so that there are not any financial barriers between us and our audience who wants to or needs to read the things that we share. So that is what open science looks like. Now, I would like to jump into some more of the tools that enable open science. So far, we've only talked about really tools that help us advance open science, but these are going to be much more in depth. And in fact, we're going to go more in depth with some of the tools that I have already mentioned. So first up, we have digital persistent identifiers. You've heard me mention this phrase a number of times. And all a digital persistent identifier is a long-lasting reference to a digital resource. Typically, it is machine readable, so computers can understand it. It uniquely points to a digital entity, much like a hyperlink, right, or a link or a URL that you'll receive for a computer, and it ensures that information can always be found. Some examples of digital persistent identifiers are DOIs, so that's going to be our digital object identifier, as well as ORCIDs, or our open researcher and contributor IDs, which we all should already have. If you do not have an ORCID and you want one, just give ORCID or ORCID a Google and you'll find the right webpage to get started. It is so easy to create an ORCID, and then you can actually use that ORCID to link all of these open science tools I've been mentioning. You want to create an account for OSF, you can link your ORCID to it. You want to create an account for data management plan for the DMP tool, link your ORCID to it. It helps recognize you as an individual entity. And so ORCIDs are becoming more and more common to provide identities for researchers, such that multiple tools can find these individuals and you don't have to keep inputting information that might change slightly over time. So since we've talked about DOIs and persistent identifiers, where can we actually get one? Well, you can get a DOI from your institution or your place of work. Now, this is conditional. This is conditional on whether or not they have been awarded the authority to do so. Many large institutions or large universities can actually have their own DOI registry system, and this is typically they enable researchers at their own institutions to archive their work. And remember, we want to archive work because it gives us that permanent, long-lasting reference to a digital object. And in fact, if you archive something, if I archive a data set for sharing, and I say, oh, you know what, there was a mistake in it, you don't delete the original version that you shared. Instead, you share a new version on top of that. And so your institution can be a place that can help you do this. Typically, though, this is going to be our larger institutions because you have to apply to become a DOI awarding institution. So your institution or place of work can help you out. A preprint server, bioRxiv, archive, SciArchive, so on and so forth. And most preprint servers will give you a DOI back. That means most preprint servers can be used for archiving your preprints. A journal publisher. Probably one of the more common routes that you would take if you want a DOI. You go through that formal review process, peer review, and then you publish in an open access journal, which I know we're all thinking about doing for our next paper. But that journal publisher will typically give you a DOI such that they'll give you a link that can always bring you back to this article that will not break. That's what citing other sources is built on top of, is making sure that I have a link to this thing that doesn't break. And then you can also use archive repositories. So this is going to be our tools like Zenodo. So let's go ahead and make one. Now, it's very easy to get started with Zenodo. In fact, I'll bring us back here. If you go to sandbox.zenodo.org. Now, there's two websites here, right? One is zenodo.org, and the other website is sandbox.zenodo.org. Remember what I said earlier, that once you use one of these archive repository services, you cannot delete the thing that you have uploaded. And so you're wondering, well, Cameron, I know that this is a class that we're taking, so don't go polluting a DOI registry with nonsense just because you want to make a demonstration. And that's what sandbox.zenodo.org is. It's an exact replica of Zenodo. It's put on by the same company, CERN in this case, and it lets you create digital objects and upload them to their service that's perfect replication of the traditional Zenodo.org experience. But the DOI that you get back is fake, meaning it doesn't resolve, and the thing that you upload is not indexed and then permanently available for access. And so what I would go ahead and do is I would get logged in. I'll log in with my org ID here. And since I'm already logged into this browser on my org ID, I was hoping that it would sign me in, but it looks like it's still prompting me here. So I'll go ahead and pull up my org ID information and get that entered. And then we'll go ahead and create this upload here. So just going to enter my org information here, just like that. We'll start with the password. And then there's my email, and I'll sign in. Oop, that doesn't look like that was the correct one there. So just make sure that's right, and that's good. And if we can't get signed in, that is A-OK as well. That seems pretty high there. Let's give another try here. There we go. Sometimes typing can be the nemesis of signing into these tools. So we'll just manually do this. We'll give this one final try. And if I'm not sign-inable through here, maybe it's because I'm signed in with Google. So let's give this a go here. Sign in there. Perfect. Okay, so Gmail, just like this. and that. All right, well, if it doesn't want to let me get signed in for whichever reason here, to link my Google account in this case, that is A-okay, because I know how easy it is for us to actually use this tool in particular. So once you get signed into Zenodo, what you would do here, maybe I have a Zenodo, actually I might already have a Zenodo account. Here we go. But once you do get signed in, and I'll sign in with GitHub actually in this case, since I know I have a GitHub and I know that this works. So I'll get signed in here, but we're going to be effectively creating a new upload or a new archive in this purpose. So you'll come to the plus button, you'll click New Upload, and then it's just another kind of step-by-step prompt. The first thing, though, is that you say, well, what files, what digital objects are you going to upload, and should they be publicly visible or not? Then you go about filling through all of the other relevant metadata. So they ask if you already have a DOI for this upload. So if you have maybe a related publication or a publication that this data is particularly used for, or if you have uploaded it somewhere else, you can reuse that DOI such that it can be easily and unambiguously cited. Then you'll have your resource type. So if it's a data set, if it's an image, if it's a lesson, see all these things that you can get DOIs for. These are work, these are things you're already doing. You create a title, publication date, so on and so forth. There's a lot of metadata here for you to fill out, and I would encourage you to think deeply when filling it out. But once you do fill all of this out, you can simply upload your work, and you get a DOI back. That provides all of the non-breaking link so that other people can cite this and other people can access it and use it. And of course, the things that they do access are just going to be the files that you upload here. So that's how easy it is to get started with Zenodo. And I will say Zenodo also allows you to search the record. So if I wanted to find something about rainfall, I could absolutely search rainfall in the search bar here. I can filter down to publications or data sets or presentations here. So maybe I'm just looking for a data set on rainfall. I can use hopefully any of these or some of these. So that is how you can use Zenodo. It is quite easy to get set up. Again, all you need to do is make an account. You can get uploading and you get DOIs in return so that other people can reuse and cite your work effectively. Our next tool, in addition to our search and archive repositories, we have programming languages. Now, programming languages are very important because they help the reproducibility of our very own work. So I've listed a couple of common programming languages here. We won't go too in-depth for these since they're a little bit out of scope for our topics that we want to cover, but just know that very commonly people use Python and R. One thing to watch out for is I would make sure you're using languages that are free and open source. The reason being is because I can write some Python code, and as long as you know the version of Python that I used as well as the packages I used, you can also run that Python code. However, I could also write some MATLAB code, and then I could share that code with you and you can read the code, but unless you have or own the MATLAB license, which is expensive, you won't be able to execute that code. So it doesn't really help for reproducibility if you are using a proprietary tool that requires some type of financial motivator in order to get started. So I would watch out for languages or tools that are proprietary and tend to lean towards more free and open source tools, ensuring that other people can use them, access them, reuse them. But why should we use programming and coding in the first place? Well, the biggest reason is probably going to be automation. You can automate all actions that you want to carry out in a uniform and consistent manner. So I have an experiment, or I was a part of an experiment back when I was an undergraduate, way back when, where I had to do some pre-processing to some data. As part of this, I had to go through a graphical user interface. And I am not kidding when I say that the lead investigator for this project printed out probably 15 pages, right, of a document that they created that had screenshots and arrows and things you need to click on, drop-downs you need to select, buttons you need to check. And then they trained 5 other research assistants to also do this. And I always wonder, right? Were we all clicking the same options every time? Did we ever get tired and misclick one thing? And this is something that automation can do, because even if there's a mistake in your analytical code, you know that that mistake has been applied uniformly in a consistent manner across all of its inputs. Therefore, changing it in that one place and rerunning it or reanalyzing the data, pre-processing the data set, you know that you'll have a correction also applied uniformly and in a consistent manner. Programming also helps us with reproducibility so that others can recreate or run your work from original inputs. You also have preservation because your code is a written record of transformation and collection. This is a huge part of being transparent. It's a huge part was why I'm a stickler for uploading code alongside a publication, because you can tell me all about your analytical your analysis in your method section, but I'm not actually going to know what you did step by step by step unless I actually look at your code. And so this is the way that humans describe things to a computer to tell the computer what to do. And then humans, we use this other language for telling other humans what we did. But for me to know what you actually did, I should be able to read what you told the computer to do. And so that's what code gives us, is this idea of preservation. We also have quality because code is an artifact that can be reviewed and improved by others. Additionally, this brings us into collaboration. Code serves as a common language. I'm not an astrophysicist. However, I have absolutely helped with code reviewing Python code for astrophysics projects. And because I have that ability to read and write in a programming language, I have this increased capacity to collaborate with others in an interdisciplinary fashion. Finally, there's also this issue of scalability. Typically, our programming languages are going to help us scale with computational models or methods and data sets that are larger and more complex than ever. And our programming tools will also scale alongside those more complex questions or data sets that we work with, whereas our tools like Excel tend to not scale with massive data sets very well, or if our problem is non-tabular to begin with. And additionally, Excel requires a license, proprietary tool. We've talked about that. So these are all reasons why you should use programming and coding in your work. Now let's talk about a flip side, or the other side of the coin of coding and programming, right? We have this long written transactional record of things that we do, but these things also tend to change over time. And this is where version control comes into play. Now, version control is very important, right? And I'll use a text-based document as an example. And that text-based document is going to be a Microsoft Word document. It's an XML document, bear with me, but we have this Microsoft Word document. And maybe I'm writing up a draft of something I want to publish on. And you can think, when I first send this paper to my advisor, right, it's titled, the name of the file itself is paper_final.docx. And it's a beautiful short file title. And then my advisor edits it, and they send it back to me, and now it's paper_final_advisor edits. And then I include or reject edits, or I make some comments and say, I disagree with that, I agree with that. And then all of a sudden, we end up with a file title that looks like this: paper final v2 cr edits for advisor edits 5. I promise this is really the final version of this thing, .docx. And it spirals out of control. And one important thing that we have lost along the way is what we changed and why we changed it. Because if you have 20 files floating around, all with slightly different names, you're never going to know which ones came first or second, or even if you did, you're not going to want to investigate what change was made when and why. It's going to be very hard for you to do. So let's jump into this next scenario here where we share a Google Doc, because it's the modern day and age. We have better collaborative tools than just a docx file. Google Doc, which we can share with advisor collaborators, makes it easy to collaborate specific sections of a document. Anyone can edit it, which is a good thing for the most part. But what if you need to collaborate across multiple documents? Because you can think, if I have a paper that I want to publish and I have some code that I also want to release alongside that publication, and after I've written up some draft of the paper, I realize there's an error in the code. I then need to make a change in a code file, and then I need to recreate some results, and then I need to make a change in my final output. And now, If you're like me and you're thinking, well, I make the change and then I have to rerun the analysis, and the analysis could take, 6 hours to run. So what I like to do is I get the code to run. Hopefully it doesn't error out, and I go to sleep, and then I wake up the next day, and then I make that edit to my paper. And now what you're thinking is, well, if we use Google Doc for this, I have a change in code, which is going to have a timestamp of, sometime at night for its last change. And then I change my paper the next day, and now I have a change in my paper related to sometime the next day. I'm never going to be able to go back and link those two together unless I have some type of a priori knowledge about these things. And so Google Docs versioning falls a little bit short because it doesn't let us very easily tie together changes across multiple documents to say that these are actually one and the same or semantically related to one another. And then the final stipulation for Google Doc is they have the suggesting versus the editing mode, and sometimes our collaborators like to use the editing mode instead of the suggesting mode, and then you lose a little bit of information as to what used to be there. Because the version control systems only updates, I think, every minute or so by default. But you can also collaborate on GitHub. Now we have a couple of tools that we use for version control, particularly for software tools or for programming. And that's going to be Git, and then we share Git repositories on GitHub. So this is an idea we'll talk about a little bit more, but you can share a GitHub repository with your advisor and collaborators, and you can collaborate and edit specific sections across many documents. And what I like about GitHub is that all edits are suggestions by default as part of the pull request process. And so we use Git, or I personally use Git, and many of us who collaborate on code use Git. And you can think about Git in this fashion. I'll mention the word Git repository. All a Git repository is a folder with a bunch of files in it that are all under version control. Meaning there's a program that kind of watches these files for change, and anytime a file changes, you can investigate, what was the change and when was it made. And then you have this idea of a commit, which is really just a snapshot or like a copy of all the files in that folder at that point in time. And so I can make changes across many documents and hold off. I don't need to commit them just yet. I can make changes to 4 documents all under the same folder. And then I can say, okay, all of these changes across all these documents are going to go in the same commit or the same snapshot. And now I have that semantic linking of different changes across multiple documents. When interacting with Git, we typically use a couple of verbs. Here are some of the most important. There's many more than this, but these are the most important. Your Git status. It addresses the question, well, since my last snapshot, do I have any pending changes that are not yet part of a snapshot? To add a Git add means that if I were to make a new snapshot, I'm not going to yet, but if I were to make a new one, I want to incorporate this file, and that file. Now, a git commit is a verb as well as a noun, thank you to the English language, but you can also use commit as a verb, which means creates a snapshot of the files that I have added, as we just talked about. And then finally, we have a git checkout, which means take me to this specific snapshot. And what this does is it lets us time travel through our version control. I can open up and I can see all of these snapshots that I've taken, and every snapshot you make, you're going to create a message, a little message, a reminder to yourself saying, I created this snapshot. You'll know the time and date that it was created, and you're going to have a message saying this was created for reasons X, Y, and Z. So we have all of this relevant metadata. We have a timeline of all the changes across our project, and we can go to any points of those times using our git checkout. So that's Git as a version control tool. In theory, it's a fairly straightforward thing, but I will say its use has a little bit of a learning curve. And so oftentimes people will reach for not the Git command line tool, which I like to use, but they'll reach for graphical user interface tools to help them get started. One very popular thing if you're coding is you can use the Git version control tool that integrates into VS Code if you're using VS Code, and it's pretty handy and easy to get started with using that. But we also will see Git-related concepts, some of those same nouns and same verbs on a code repository. Now, this is a GitHub repository for Seaborn, which is a statistical data visualization tool created by Michael Wascom, and this is hosted on GitHub. And what I just explained to you earlier about Git, those are all things that you can do on your own local computer. And that's good for your own personal notes. But how do you collaborate with other people? That's what you use GitHub for. So you can think GitHub is like a cloud-hosted Git repository. And how you interact with that is I have a copy on my own local computer, I have a copy on GitHub, and I can push changes from my local copy up to GitHub, and I can pull changes from GitHub down to my local copy. So you have one-way synchronization in either direction. When you go to a GitHub repository, you're going to keep an eye out for a couple of things. You're going to look for, well, is this a tool that I actually want to use? Do other people use this? How well updated or well maintained is this tool? And you can answer these questions through the use of various GitHub properties like stars, the date of the last commit or the date of the last snapshot. Are issues being open or closed? Are pull requests being open or closed? And are people contributing, as well as are people creating copies of this thing for them to work on? But I think we'll take a quick look at a GitHub repository, or at Michael Wascom's GitHub repository. So I'll go ahead and pull that up. Well, GitHub Seaborn Python, and you can take a look at this GitHub repository. So if I were to assess this repository for health, meaning how actively is it maintained and updated and regulated, I'm going to look at a couple of things. I mentioned the stars. That's kind of like our likes on GitHub. And so if you're on Instagram or Twitter or LinkedIn, right, and you have a like on your status, then that's going to be the equivalent of a GitHub star. 13,000, that's quite a lot of stars on GitHub. So this is at least a popular project, or at least it was at one point in time. Forks, if I want to actually collaborate with the proprietor or the maintainer of this repository, Michael Wascom, I can't go and change his files, right? There's a lot of permissions that don't let us do that. And you can think, if I'm working on a project, how annoying would it be if anybody from the internet could just come and change whatever they wanted? Instead, what we do is we make a fork, which is just a copy of that project, but it lives under my profile. I can make any changes that I want on my profile. And then once I've made changes under my own profile to my own copy, I can then open up what's called a pull request. And I say, dear Michael Wascom, I've made these changes. Do you like them? And can we incorporate them into the project? So that's our pull request. We also have issues. Now, issues are, I think I found a bug in this project and I want to tell somebody about it. You can open it up on an issue. And those are the things that we typically look for repository health. How many stars does it have? How many people are forking it? How many issues have been recently opened and closed? How many pull requests have been recently opened or closed? Additionally, there's also the date of the last commit. We can see that Michael Wascom did something maybe 3 hours ago, and you can see his commits there. Once we get past the markers of a manicured repository as the properties, we can talk about the files that we will find. So if you've never been to a GitHub repository, this is going to be very, very important to read because it's going to give you sources to go to when trying to discover things about the code that's in the GitHub repository. We have a couple of things. We have documentation, legalities, collaboration, credits, and history. And so the documentation, the best place to start if you want to find out about a GitHub project is to go to the README, which you can just scroll down and see at the bottom, or I can click on the README file if I can find it here. So all of these little icons that you see here, these are folders and these are files. And if I want to look at any file, I simply need to click on it. The README is one of those files that GitHub has deemed so important that I don't even need to click on it. GitHub simply puts the README at the bottom of the page here. The README is going to answer a couple of questions for us. What is the project? What does it do? How do you install this? How do you use this? Why would you want to use it? How do you get involved with maybe collaborating? And maybe it'll link out on that. And how do you get involved with testing it? It also gives, in this case, a guideline for citing it. And that's another piece of metadata we'll talk about in just a moment. But that's the important features of the README. Next up, we also have the license, which in this case you can find in the license file. But again, GitHub thinks it's so important that you can find the license, so you can click on this little navigation tab here next to the README. And this has the actual license that has been included with the software. So it tells you what you can and can't do with the software. It tells you if you can redistribute it or not, and if you can, what legalities you need to abide by. So that's the purpose of a license. Next up, we also have the citation.cff file. We have to click on this one because GitHub hasn't deemed it so important in a functional manner just yet. But if you click on this file, you can see that it's simply a file containing metadata. You can see that this is a message from Michael Wascom to us saying, if seaborne is an integral part to a scientific publication, please cite using this metadata here. The preferred citation is an article, so this is hinting to me that Michael has published on this. It tells me that Michael is the sole author. Here's his ORCID, as well as first or family and given names. Here's the DOI, back to that digital resource, and we can actually resolve this DOI. I'll show you how to do that. If you quickly go to doi.org and scroll all the way to the bottom, there is a small input or a search box that you can paste any DOI into. So I'll paste that DOI from Michael Wascom's project and click Submit here. And when I do that, you'll see that I go right back to the publication. Seaborne is statistical data visualization. This was published in the Journal of Open Source Software. And we'll see this information actually repeated in the citation.cff file. Where was it published when? This is all where you can find all the metadata relevant if you want to cite this project. So it's a very handy tool to use, or file to know about, the citation.cff file. And that more or less sums up the important files that we'll take a look at. There's also going to be the contributing file as well as the change log, which you can find if you poke around GitHub a little bit more. The contributing file is if you want to contribute to this project, write code for this project, then here are some guidelines that you should abide by. And this is an important file to include if you're planning to collaborate. The change log, you can look at all of the different snapshots. And if we take a look at this, we'll see it's a little bit too fine-grained, right? Fix tick visibility, introspection on 3.10, pin MyPy, try pinning pillow to fix the eye. As a user of this tool, I don't care about these really small changes. What I do care about are the large changes. And Seaborne keeps its change log on its documentation website. If you go to its documentation and click on releases, you can find the large changes for every major and minor version release. And these are the changes that a user, somebody using this tool, will likely care about who doesn't want to also be a contributor back to the tool. So that's the important files to keep in mind for GitHub. Now, remember that our FAIR acronym applies to everything. And in this case, our metadata support FAIR. Our documentation, our README, helps make things more reusable and interoperable. Our legalities or our license file makes things more reusable. Our contributing file makes things more interoperable. Our citation file makes things more findable. I will say the citation.cff file is indexed by Google to help you find things that you're looking for. The change log helps things be more interoperable because other people can come to a more rapid understanding as to what's different compared to a previous version. And then finally, the fact that you put it on a GitHub repository in a publicly accessible manner means that this thing is more accessible. So every piece of metadata that we've seen help us support FAIR when sharing code. Now, there's a couple of guidelines I want to share. We can go through these pretty quickly, but we have documentation. There are guidelines for writing good documentation, and typically the suggestion is that you should split things up evenly between tutorials, how-to guides, explanations, and references. For a license, you can absolutely, for a software product, you can use a website called choosealicense.com. But remember, a license is just a file or some text that tells you legally what you can and can't do with a given resource. For additional software licensing concerns, I would absolutely recommend that you check out one of my colleagues' courses on licensing, Lorena Barba, and you can find this at gw-ospo.github.io/OSS licensing. For collaboration, here's some guidelines on creating a contributing file. So this is going to help you get started with building up a file that will inspire others to collaborate and what you should keep in mind when you're asking other people to collaborate. Because the worst thing that can happen is I think something for maybe Michael Wascom, right? Maybe something for Seaborne. I create something that I think is so cool. I spend 3 days of my life working on this, and I open up one of those pull requests, and Michael Wascom takes a look and says, nobody asked for this, so I don't want it. And then I sit there and I say, oh man, I wasted three days of my life. So what I should have probably done is checked out the contributing guideline and read that for new features, we should have a discussion in the issues section of GitHub first to see if this is worth putting effort into. So contributing guidelines for considerations like that. We also have the changelog, which we saw the snapshot or the commit history, which is just a little bit too crowded. And so we reach for something like a human readable changelog. And I can't recommend enough, keepachangelog.com if you want just some basic guidelines for how you can keep a human understandable changelog, something that's very important when creating and collaborating on code. We also have the citation file, the CFF file, citation.cff. You can create these. This is actually a file format created by inmain created. So you can check out citationfileformat.github.io for extra information. There's also on that website, you'll also find a very easy to use tool, as we've seen many tools, to create a citation.cff file. All you need to do is go through it and plug in your information, like your family name, given name, org ID, the title of the thing, its type, is it a software, is it a data set, and other relevant metadata, and you can automatically generate one of these files to include in your project. As part of this file, one thing that I really like about the citation file is that it supports credits, contributor role taxonomy. Credit.niso.org provides 14 different roles for you to disambiguate what people actually did. And if you've ever seen or been on one of those papers that has 100 authors, because there's so much effort that goes into the data collection, the curation, and all of the effort needed to produce this publication, and everyone has some requirement to be listed as an author. Well, we know for a fact that if there are 50 authors and it's a 50-page paper, that not everyone wrote a single page, and then you glued them all together at the end. More than likely, right, the lead author wrote something of a rough draft, maybe a couple of others made significant writing contributions, maybe the last few authors, right, the advisors made some reviews and edits, and all the authors in between maybe had some marginal contribution that was significant because it enabled this work to be done, but it wasn't actually part of the publication process. And so what Credit has done is created these 14 different contributor roles, like conceptualization, data curation, funding acquisition, investigation, methodology, writing, visualization, validation, so on and so forth, such that for every single person listed on your paper or on your article, you can say this person contributed in this fashion. They helped with software. They helped provide resources. They provided supervision. Whereas maybe this other person was somebody who helped with conceptualization and methodology and helped write the original draft or perform review and editing. So I really do enjoy the contributing role taxonomy, and citation.cff files support this, which is amazing. Citation.cff files support a ton of metadata. It's much more than just this as well, and I would highly encourage you to check out the citationfileformat.github.io website. So we have talked a lot about tools that enable open science. We have our digital persistent identifiers that help us with findability and reproducibility, because you can always go back to that link because it always works. We talked about pre-registration for transparency purposes. We've talked about programming languages for reproducibility and collaboration. We talked about version control for transparent development and interoperability, code repositories and archive repositories, all for both findability, permanent storage, public access, DOI linkage, and findability, as well as contributor role taxonomy for more transparent collaboration and work practices. And finally, something we mentioned a while ago, are search portals for the findability of relevant data sets and publications. These are all tools that you can start using today. I will say some of these tools, like version control through Git and GitHub, they're going to have a slightly higher learning curve than some of these other tools. And so that leaves us with one final question. How do I participate in open science? And before we wrap up today, I just wanted to outline a couple of ways that you can get started based on the things that we have seen today. First and foremost, create an ORCID account. You should have already done one, and if you want that NASA TOPST Open Science badge, you need an ORCID. So make sure that you have an ORCID, because it will help identify you as an individual researcher at an institution. You can also analyze an existing data set that's been shared. And we saw an example on datasetsearch.research.google.com how we can find a data set and what considerations we should have when going through data for reuse, right? Do we know do we know where it came from? Do we know what has been done to it? These are all questions we want to know the answer to when we're using a tool like datasetsearch.research.google.com. You can try to reproduce a fellow author's or your own work. And I will say I've met many people, myself included. This happens all the time. You think back to a study you did a number of years ago, and you're thinking, oh, where are those data? And then you find them, and you look through the code, and you think, I don't even know if this will run, and it doesn't run. And so try to reproduce your own work. Try to reproduce a fellow author's work. You can write that up as a publication if you do reproduce somebody else's work. You can pre-register your next study. You can get started at osf.io/prereg. You can publish in an open access journal. We talked about the doaj.org website, which helps you find open access journals within your field and beyond. You can also, for your next publication, assign contributor roles for your collaborators using the credit taxonomy. Many journals are starting to support this and encourage this, so definitely check out this taxonomy. You can enhance your reproducibility of your work by using a programming language and including code for analysis as part of that publication. And importantly, you can permanently share those analytical code, you can permanently share those data that you collected with your next publication using a tool like zenodo.org that will help you archive permanently the things that you create so that others can use them, make reuse, and download and work with them. And if those all seem a little bit too big, most of them are creating accounts and then filling out step-by-step guides. And so if you're still not sure how to get started, I would highly recommend checking out the Open Science Foundation, osf.io. It truly is a one-stop shop for, or I will say an all-in-one tool to get started because you can plan and pre-register your research project. This is the same OSF, Open Science Foundation, that I showed you how to pre-register through, but you can do much more than just that. So you can plan and pre-register, you can actually publish a preprint, they have a preprint server, and you can make transparency a priority. But with all of that being said, we have addressed 4 fundamental questions going from why is open science important, then envisioning what open science looks like, talking about a lot of the tools that enable open science, and finally talking about how you can start being more open and more transparent in your work. I want to thank you all for taking the time to discuss open science with me today as part of our open science skills makeup. My name is Cameron Riddell, and I hope to see you all and hear from you all sometime soon. Thanks, everyone, and I'll see you around.